This is the screencast for section 2.4, example 7. So we're going to find all the real zeros of a polynomial function, and we're not going to use our calculator entirely to do this. So first of all, we have two types of real zeros. There are rational zeros, which are zeros that can be written as fractions or also terminating decimals, so like 1.2 can still be written as a fraction. Irrational zeros are zeros that are non-repeating, so like 1.2222222 forever and ever can be written as a fraction, but if it doesn't repeat, so 1.1546198, you get the idea, and doesn't end, those are irrational. So for example, like the square root of 2 would be an irrational number. So how do we get started with this? Well, you have to use your calculator to get started. You got to find the actual zeros first. So basically, in a problem like this, you will be graded on your work shown, not just the actual zeros you find, because your calculator can find the zeros for you. I want to know that you understand what process we're about to go through using synthetic division, factoring, and you'll see some quadratic formula in here. And basically a breakdown at the end. So here we go. I did some work ahead of time. I found a good window for the graph. I found the 4 zeros. I can see that 4 and -1/2 are rational zeros. I can easily plug those into synthetic division. So I'm going to start with the easiest one first. I'm going to plug in 4. So 4 into synthetic division, I have to write out the leading coefficients. So I drop down 2, 4 times 2 is 8, -7 plus 8 is 1, 4 times 1 is 4, -8 plus 4 is -4, 4 times -4 is -16, 14 minus 16 is -2, 4 times -2 is -8, and I get a 0 at the end. I should get a 0 at the end. I'm looking for a 0 of the function. It should have remainder 0. The other part of this, what this means, is that you took the original function, you took 2x to the 4th minus 7x cubed minus 8x squared plus 14x plus 8, and you broke that function down into 2 parts. So I need to see this breakdown off to the side of your work, of your synthetic division. What you now broke this down into was the binomial where k is 4, so x minus 4, times what you got, the leftovers. So that would be, let's see, -2, then -4x, then 1x squared. So 2x cubed plus x squared minus 4x minus 2. So you have begun factoring. Now you've learned several different ways of factoring in the past. You've learned quadratic formula you can factor, you've learned to unfoil something, you've learned the sum product method. I mean, factoring has been this process that's been very complicated, but here you can use synthetic division and factor something that has 5 terms in it, something you've never been able to do before. So basically, if you took x and multiplied it back out through all the 4 terms in the second part here, and then took 4 and multiplied it all out, combined like terms, you would get the original function. Our next step is to continue the breakdown. We want to keep breaking this function down. We don't want to start over and break it down a new way. So we're going to work with this piece, the 2, the 1, the -4, and the -2, which are already written here for us. And we're going to use our next rational 0, which we said was -1/2. So we're going to use -1/2 and go through synthetic division. Drop down the 2. 2 times -1/2 is -1, so 1 plus -1 is 0. -1/2 times 0 is 0, so we have -4. -1/2 times -4 is +2, so we end up in a 0. With one less term, we're not using the remainder from the previous one. So now our breakdown, we've broke down this original polynomial even further. We have the x minus 4 from before. Now we use the k value negative 1/2. That does not mean you use x plus 1/2. We don't use fractions in our factorization. We instead use 2x plus 1. So in other words, if you plugged in negative 1/2 for x there and multiplied by 2 and then added 1, you would still get 0. So we do not use x plus 1/2. We would use 2x plus 1. So basically you're changing the leading coefficient there. What was left over then was, let's see, a minus 4 and then 0 x's but 2x squared. Well, I don't have any other rational zeros that I can put into synthetic division and continue to break that function down with. So instead, I'm going to off to the side do 2x squared minus 4, set that equal to 0, and see what I can find as the other zeros. So I'm going to factor out a 2, divide both sides by 2, and I get x squared minus 2 equals 0. Add 2 to both sides, x squared equals 2. Now take the square root of both sides. Don't forget that plus or minus. So x equals plus or minus the square root of 2. Now if you check in your calculator, the square root of 2 is 1.414214, etc. So we did find this is the negative square root 2, this is positive square root 2. But again, you're going to be graded on the breakdown of all of this algebra. So our concluding statement can say f of x equals our first piece we broke down, x minus 4, times the second piece, 2x plus 1, times, now we have the 2 that we factored out in front. So I can put, actually I should probably move that out in front. Then at the end, I've got x minus square root 2 because k could be positive square root 2, and then x plus square root 2 because k could be minus or negative square root 2. So to find all the real zeros, the zeros are x equals 4, negative 1/2, positive square root 2, negative square root 2. And all of those comma 0. So 4 comma 0, negative 1/2 comma 0, square root 2 comma 0, and negative square root 2 comma 0. The now try problem for example 7 is number 49. We need to find all of the real zeros of the function, find exact values whenever possible, which is always possible. Identify each zero as rational or irrational. So there's an extra step we're going to follow on this problem compared to the last one. So number 49, I again graphed this ahead of time, found a good window. I found all of my zeros. Be careful, there are 2 zeros right here next to the x-axis. My first clue was I saw the negative 1.414 just like I had before in the previous example. So and then I found that. But also as I traced along the function, I saw my y values go from positive to negative back to positive. So I could be sure that there was an extra 0 in there. Also, if you zoomed in, you'd be able to see it. So now that I have 2 irrational zeros, which I can pretty much predict are negative square root 2 and positive square root 2, but I need to show my work. So the other rational zero I have is 3 halves. So I will put 3 halves through synthetic division. Drop the 2. 3 halves times 2 is 3. Now I have negative 3 plus 3 is 0. 3 halves times 0 is 0. Add, we've got negative 4. 3 halves times negative 4 is negative 6. And then I have a remainder of 0, which is good. That's what I need. So what I have done off to the side is I have taken the original function, 2x cubed minus 3x squared minus 4x plus 6, and I have broken that down into 2 pieces. The piece I just got with k being the 0, so x minus k. Again, we can't do x minus 3 halves, but you can do 2x minus 3. Then the other part I broke that down to was 2x squared minus 4. Sound familiar? So now off to the side, I don't have any other rational zeros I can do in synthetic division, so off to the side I'm going to see what happens to 2x squared minus 4 when I set it equal to 0. So I will factor out a 2, divide both sides by 2, x squared minus 2 equals 0. Now I'm going to add 2 to both sides, x squared equals 2. Now I'm going to take the square root of both sides. Remember the plus or minus, so surprise, surprise, x equals plus or minus the square root 2. So now I can break down the function even further. I've got the 2 that I factored out in front, the 2x minus 3 that came from when k was 3 halves, and that was a perfect it worked out perfectly in my synthetic division, no remainder. Now I have x minus square root 2 and x plus square root 2. So there is my completely factored f of x. F of x totally broken down into binomials is 2 times 2x minus 3 times x minus square root 2 times x plus square root 2. So the zeros are at x equals 3 halves, which is rational. It can be put into a fraction. And x equals plus or minus square root 2, which are both irrational. They are non-repeating, non-ending decimals.